Last time we were showing permanent in VNP. Any questions? So there were some questions after the class, and there is a small mistake. So recall this definition of G, right, which is basically a product of the row sums. So these are the row sums. So you are multiplying n of these row sums, and so in the claim, when we are showing that sum of these products is permanent, sigma product is permanent, uh, what we should correct here is suppose the monomial we are looking at is x1 I1 x2 I2 dot dot xn in. Say R is the number of distinct subscripts. So let R be the number of distinct elements in this set I1 dot dot in. Okay, and then so after this the calculation here will not be 2 raised to r minus 1, but in terms of n minus r. Okay, so we'll just change it to this 2 raised to n minus r, and this is over n minus r. And then as long as r is less than n, this sign will be 0. This will come out to be 0 as r is less than n. And if r is equal to n, then it means that I1 to In are distinct. Okay, so in the distinct case, you will get the monomials corresponding to permutations, and they will come with sign 1. So that is exactly then computing permanent. Okay, so with this correction, let us proceed. Right, so now let us write down a conjecture which was made by Vaillant. So it's called Vaillant's hypothesis. So it is his hypothesis, which means which is still unproved. So it's a conjecture, Vaillant's conjecture. This says that VP and VNP are different. Okay. So again, VP is the set of those polynomials that can be computed by small arithmetic circuits, and VNP is the set of polynomials that can be written as a big sum of small arithmetic circuit. And Vaillant's hypothesis claims that these two are different things. Okay, so obviously VP is in VNP, so the conjecture is saying that there is a polynomial which you can write as a big sum of small circuits, which cannot be written as a small circuit, okay, overall. And we will not be doing that proof, but permanent is essentially VNP complete. So this alternately you can say that permanent polynomial is not in VP.
Here in completeness, how do you define the reduction?
The reduction will just be is there a polynomial in which if you set some variables, you get your favorite polynomial? Projections. By projections, and yeah, where the bigger polynomial should have a small arithmetic circuit. So is there a small arithmetic circuit which on fixing some variables gives you your polynomial? So permanent is not in VP. This is an alternative formulation of Vaillant's hypothesis. So these questions are the central questions in algebraic complexity theory, and even in complexity theory because of the following connection. So if you look at permanent of a Boolean matrix, 0, 1 matrix, suppose this 0, 1 matrix is it is the adjacency matrix of some bipartite graph. So that represents a bipartite graph. So let us draw a small example. So say you have 3 vertices on each side. So 1, 2, 3 here, and 1, 2, 3. This is left side is u, right side is v. So how do you represent it? As a Boolean matrix. So it will be a 3 by 3 matrix where 1 comma 2. So 1 comma 1 will be 0, 1 comma 2 will be 1, 1 comma 3 will be 0, 2 comma 1 is 0, 2 comma 2 is 0, 2 comma 3 is 1, and so on. Right. So this is the matrix that represents this bipartite graph. So u, v, and the edges are in the middle, E. So this matrix M, if you look at the permanent of this matrix, what does it represent? Exactly. So you can show that permanent of M is in this graph G, the number of matchings in G, perfect matchings. Okay, so this is easy to see because when you look at the permanent of the matrix, you will, by definition, it is the sum of monomials, right? So every monomial basically corresponds to picking ones in those places if they are present. Otherwise, this monomial, this product will not contribute. So you can pick these ones only when there are these disjoint edges to pick. Okay, so that exactly, so every monomial product corresponds to a perfect matching. And then you are taking the sum without sign. So this gives you the exact count. So permanent of a Boolean matrix actually gives you the count of perfect matchings. So this is simply the number of perfect matchings. So yeah, so in practice, given a graph, can you compute the number of matchings? Can you check whether there is a perfect matching? Right, so checking whether there is a matching, this has a practical algorithm, which is a very famous algorithm given in the 60s or 70s. But to count them is considered to be very hard. It is harder than NP-hard problems. Okay, so permanent on even this 0-1 matrix is actually hard to compute in practice. So this is actually equivalent to the functional problem of sharp set. Okay, so sharp SAT is the problem of, it is the counting version of SAT for formula satisfiability, Boolean formula satisfiability. So given a Boolean formula, how many satisfying assignments are there? So for n variables, it can be a number between 0 to 2 raised to n, right? So even testing whether it is positive, this is the NP complete problem, and here you are asking to actually count it. So clearly this you would expect to be harder, much harder than just SAT. So there is no hope of solving this in practice. Okay, so this also is due to variance. So this is called variance sharp P completeness. Of permanent, which is Boolean permanent. So Valiant showed that the Boolean permanent, or computing the permanent of a Boolean matrix which corresponds to a graph, this is this is equivalent to SharpSat, and SharpSat defines a class which is called SharpP. So I wouldn't go into the definition or the proof of this, because this we cover usually in computational complexity course. This is to do with the Boolean word. Here in the arithmetic word, now we want to study permanent as a polynomial. Okay, so can you compute permanent as a polynomial? And obviously this should remain a hard question, because intuitively, if you can write the permanent polynomial as a small arithmetic circuit, then there is, in all likelihood, you will also be able to solve permanent in practice, right? But that would mean that you are solving not only SAT but SharpSat, right? So you are solving all these hard optimization problems if you solve this. So that is not generally believed. So this motivation then suggests that the conjecture, Valiant's conjecture, this is like the conjecture of SharpSat not in polynomial time, functional polynomial time. Okay, so it's not formally correct, but when Valiant conjectures that VNP is different from VP, which is permanent is not in VP, it is like saying that if you wanted to count the number of satisfying assignments, that you cannot do in polynomial time. Okay, so arithmetic circuit size corresponds to Boolean time or time in practice, and so you could think of Valiant's hypothesis as this. And both these things we would expect to be true, okay, but there is no proof. These are open questions. So this we call the arithmetic analog of the P different from NP question. Okay, so P not equal to NP is the classical question in the Boolean world or in the real world, and the algebraic or the arithmetic analog of it is the VP not equal to VNP. Any questions? Okay, so is there a formal connection between them? So formally there is no direct connection known, but there is a result due to Burgesser, which I will state. It's not hard, so you can even do this as an exercise. So it says that if VP is equal to VNP, then what happens?
P and P by poly.
Yeah, right. So P and NP are the same slash poly. So P slash poly is equal to NP slash poly. Okay, and I will not go into the details of this implication. There is some little assumption based on what field you are working in. But if you are working in a finite field, then this implication is exactly true. So Burgesser showed that VP is equal to VNP would imply that P slash poly is equal to NP slash poly, which is much stronger than saying P equal to NP. Well, yeah, I mean it's technically it is incomparable, but so I mean from this you cannot really deduce whether P is equal to NP or P is different from NP, because when you talk about the P and NP classes, you are talking about Turing machine, you are not talking about Boolean circuits. So P slash poly is actually the problems that you can solve using Boolean circuits, and NP slash poly is also defined in a similar way using Boolean circuits. So the meaning of efficiency in Boolean circuits and the meaning of non-determinism in Boolean circuits, these two things are the same. This is what the equality is saying. Okay, so equality is saying that non-determinism and efficiency are the same. Intuitively, we do not believe this. Intuitively, we believe that non-determinism is far stronger than efficiency. But so this is talking about the Boolean circuits, and original PNP question is for Turing machines. Okay, so on the left hand side you have arithmetic circuit statement, and on the right hand side you have RHS, you have statement about Boolean circuits. So this is pretty satisfactory, although not completely satisfactory, but it suggests that if you want to show P different from NP, then you should first show VP different from VNP. Okay, you cannot just most probably you cannot skip this step. In fact, it shows something far stronger. So you may or may not know the definition of this class, but Burgesser also shows, his proof also shows that this is in NC3/poly. So do you know what is NC3 or what is NC? So these are Boolean circuits where the depth is only log cube. Okay, so this is again this exactly models very fast parallel algorithms. So on an input size of n, the parallel time complexity is only log cube. Okay, so it is exponentially faster than what you would expect. So if you show VP equal to VNP, then Burgesser's proof actually tells you that NP/poly is not just equal to P/poly, it's even equal to NC3. So non-determinism is the same as efficient parallel algorithms. You can solve, in a way, it is saying that you can solve SAT in parallel, fast parallel time. Okay, so everything on the RHS is actually unbelievable, and hence LHS is also unbelievable. That is the import of this implication. When you are working over characteristic 0, then Burgesser's proof requires the assumption of GRH, generalized Riemann hypothesis. Okay, so this is why I put an exclamation mark. But that is not very important. So I think everybody in this class believes GRH, so you don't have to worry about those specifics. Right, so let us now move to easier problems than VNP. Is there any question? Okay, so the easier problem we will move to is determinant. Okay, so where is that? It's in VP, right? So what is the proof of that? So let us now place determinant in VP. Okay, so this we will do using some classical identities from 1800s, which are called Newton's identities. So this is an old proof. Once we have done this, we'll also see a modern proof, which will be far more efficient and cleaner. But the first proof of determinant in VNP was this that I'll now present using Newton's identities. So what do you want to compute? You have a fully symbolic matrix, entries Xij, n by n matrix. So we want determinant as a small arithmetic circuit. And the only thing shown in this class is the definition of determinant, which requires n factorial monomials. And here now we want poly n sized arithmetic circuits, right? So what is the plan? The plan is to write determinant in some other way. which is not too big, and then implement it as okay. And so this arithmetic circuit will be computing determinant as a whole. It will not be evaluating values of determinant. It will be actually computing determinant polynomial, which is very different to what you do when somebody asks you to compute the determinant of a matrix, say of entries 1, 2, 3, 4. Okay, so there you do Gaussian elimination and you get a number, but that is not the same as saying that you have computed determinant polynomial as a whole. So we'll now achieve that through identities. So let me anyways write that down. So Gaussian elimination uses, the problem is that it uses division and many other things. Uses division, permutation, if then else, etc., that we cannot naively write as a polynomial. So it is using non-arithmetic operations. Okay, so that doesn't apply to our current problem. So here I will present Zanki's idea. So Zanki's algorithm, it's an old algorithm. The idea here is what is the relationship of determinant with the eigenvalues? Yeah, so that is the idea, that determinant of the matrix is equal to product of the eigenvalues. So eigenvalues of x. Now we would not worry too much about where these eigenvalues live, because they live in a complicated place. Your matrix X has just formal variables as entry. So if you try to compute eigenvalues, they will not be complex numbers, they will be actually complicated functions in these variables, and technically they are in the algebraic closure of the function field. Okay, so we should not worry about its representation, and that will be an amazing thing, that without worrying about the specifics of lambda I, still they will help you in getting an identity that will be very explicit. Okay, so let us just start with this. This is the first identity, and what is the plan after this? So the plan is to express it as a polynomial in the power sums. So power sums means well, let's say sigma lambda I, or sum of the squares of lambda I, or sum of cubes, and so on. So these are the power sums. So as a function of the power sums, you want to write the product. So you must have seen this. Sorry.
Characteristic polynomial.
What do you mean characteristic polynomial?
Roots of that are lambda.
Right.
We can write
Any
symmetric function.
Any symmetric polynomial, you can write it as a power sum.
Yeah. So it is nothing to do with the characteristic polynomial. It is just any product of anything you can express as a function of the power sums. And in general, as Abhibhav is saying, that any symmetric function in lambda i's, where lambda i's are really arbitrary, will not use their eigenvalue property. Any elementary symmetric function, or actually any symmetric function, you can write as a function of, in fact, as a polynomial of power sums. So this is the this follows from Newton identities. This you must have seen or even computed in school. Yeah, so we want to prove that in full generality. Okay, so power sums are, the kth power sum is basically the sum of kth powers. Okay, so that is pk for k greater than or equal to 0. So why can you write product of lambda I as a polynomial in pk's, where k goes up to n? Let me also add that you will not need to go beyond n. So just from 1 to n, these p1 to pn will be enough to produce, right? So this is very mysterious. It's even hard to conjecture unless you have some experience. But anyways, this is the plan. So we'll implement this plan, and let us answer the question, the next question: why is it helpful? So if you prove such a thing, can you write pk as something, some small circuit? What is the relationship of pk with x? In fact, what is the relationship of p1 with x? P1 is sigma lambda I, right? It is the trace of x, right? Exactly. So that is the beauty. So note that pk is equal to trace of x raised to k. So now this has a small circuit, because x raised to, so say k is 2. So x square you can compute just by multiplying and adding the entries. So there is a trivial arithmetic circuit that can compute x square, all the entries of x square, in particular the diagonal entries of x square, and then there is an addition gate that adds up those diagonal entries and you get trace of x to the k. Okay, so you just have to compute the diagonal entries of x to the k to compute trace, and each or any entry of x to the k can be computed via a circuit. Now, as k grows to n, what you can do is something like repeated squaring. You can just compute x square, then you can compute x square whole square, x square times. So if you have computed x square, so these are, you have n square outputs defining the matrix x square or describing the matrix x square. So you can then square it, and the same. So you can actually do this in just log n steps, this process. So even, I mean, it will ultimately turn out that even the depth of the circuit will not be too much. Okay, that is the point. So it will be a really nice circuit. Not only the size is small, even the depth is small. Okay, that is the advantage of working with pk. So to begin with, it was not really clear how will lambda I or lambda 1 will be useful at all, because lambda 1 is something very complicated in terms of x. But the thing is that it is not just lambda I, you are actually looking at the product, and the product gets related to traces, and the traces are simple for arithmetic circuits to compute. So thus the above expression would give us log square n depth, poly n size, arithmetic circuit for the determinant. Okay, so the important, not only is the size there, which is actually all we wanted. So everything else is bonus. We just wanted poly n size. That it surely will be. This you can immediately see because of the x to the k computation. The depth you will have to analyze carefully. So I leave it as an exercise. but you will be able to show that the depth is also very small, it's only log square n. In fact, this was the reason why people studied this in the 70s, because people wanted a very fast parallel algorithm for determinant. Okay, so the motivation was actually practical. So determinant is a very practical problem. In fact, all these ML companies, the only computation they do is either they multiply matrices or they solve a linear system. So if you are solving a linear system, you have to invert a matrix, you have to compute determinant. So if you can do it in parallel, so you can buy many computers and you implement determinant in parallel. Okay, so this is saying that for a huge n, if you make that kind of if you buy many processors, then after this one-time investment, you can actually solve determinant on various instances in only log square n time, once you have set up the parallel architecture. So which can be very important if you are if you want real-time solutions. Yeah, so this depth is actually the motivation why people studied it, but we currently only care about the size. So this is enough to show that determinant is in VP. Okay, so I leave the details in as an exercise. So let us do the main thing, which is connection with power sums. So how is that done? How is that proved? Okay, so yeah, we'll prove the general thing. So let us study elementary symmetric polynomials. Versus power sums. So what is this identity, whose existence is not clear? I mean, this is just some claim that I am making, but if you think about it, it is not clear why this connection should even exist. The elementary symmetric polynomial Ek on these n variables is defined as, so this would be what? Right. So k times you pick k things, multiply them, and then do this in all possible ways. Right. So it's about subsets, k subsets of 1 to n. So you pick an s, and then you multiply these lambda i's. That's it. So E1, for example, is just the sum, and then E2 is product of lambda I, lambda j for distinct ij. This thing we may sometimes write as lambda sub s. Okay, so this is just the product of lambda i's I in s. Okay, so example is E1 is equal to the sum, E2 is equal to this quadratic form, I not equal to j, and dot dot En has only one monomial, which is the full product. Okay, so these are the n elementary symmetric polynomials. Now the problem doesn't happen in the ends, the problem happens in the middle, because there you are looking at n by 2 subsets, and they are exponentially many. So that is a large sum, right? So computing those things is complicated, also in practice. So how do you make it efficient? So this is what we call in the course Newton's identity. This is a recurrence to simplify our life. So for kn greater than equal to 1, it writes Ek in terms of ek minus 1, ek minus 2 dot dot e1 and the p's, the power sums. Okay, it gives the function and it turns out to be a very simple one. So I is 1 to k. Okay, so it is just this convolution type of product of e's and p's. Okay. So this is a recurrence, which means that if you know the expression for ek up to ek minus 1, if you know the relationship with power sums, then this immediately gives you the relationship of ek with the power sums, and you only need power sums up to pk. For ek you only need power sums up to pk, you don't need anything else. Okay. So this is exemplified as, so E1 is just P1, unsurprisingly. What is E2? So E2 is right, which is then P1 square minus P2, right? And 3 is E2 P1 E1 P2 P3, which you can again write using the previous things.
A priori, it's not even clear that the power sum representation of En is succinct, right? Like it will be a
Right, but
polynomial in the Pn.
yeah, that is a good point. But remember that you have to write down an arithmetic circuit. So assuming that even to ak minus 1, you know the arithmetic circuits. On top of this, you can produce ek. Yes, that is important. Yeah, and maybe you will appreciate the fact that this actually produces a circuit, not a formula, as far as small size is concerned. Because in formula you will not be able to reuse the output, and if you have to implement this recurrence, you have to keep reusing it. Otherwise, things will start blowing up. So you really use the power of a circuit, and so more than a formula, and then you can write ek as a function of ultimately the circuit in terms of lambda 1 to lambda n. Okay, so let us do the proof details finally. Yeah, so how do you think you will prove this? It's impossible to guess this, but once I have given you this, how will you prove it? Yeah, but even induction doesn't look easy. Because what is induction telling you? It's saying that ek minus 1 is a function of lower p's. But then who will dare substitute that expression? So we'll actually give a cute proof using generating functions. So let us consider a generating function in a formal power series or as a formal power series. Okay, so the mathematical tool being used is actually formal power series. So it's an infinite sum that we'll look at. So what is the generating function for ek? So you should look at ek t to the k, but let us instead look at minus t to the k for notational convenience, and k goes from, let's say, 0 to n. Okay, so this is the generating function. There is no reason to stop at n, but if you look at en plus 1, it is already 0. So this is why we are truncating at n. But this you can think of as an infinite sum, goes beyond t raised to n, and so this is the generating function of the e's. There is another way to write this. You can factorize this to get what?
1 minus.
Exactly. So you know that the roots of this polynomial by fixing t are lambdas, right? Or 1 over lambdas, kind of. So you can actually factorize it as 1 minus lambda I t. Is that clear? So just you can check this. This just follows from polynomial multiplication. You just look at the RHS, and the way you multiply polynomials, you will actually get elementary symmetric polynomials, all these EKs, and yeah. So now this is a good identity to start with to get a recurrence for EK. So do you remember the high school method of getting recurrences? Yeah, you have to differentiate. So you differentiate and then you will be done. So basically apply the operator again. For notational convenience, we will apply t times dou t. Okay, so we differentiate and scale up. Differentiate and scale. So what is the result? So this will, on the LHS, this will give you sigma k e k minus t to the k right, and on the RHS you will get, so on the RHS you had a product. So when you differentiate it using, you can use the Leibniz identity, which is you differentiate one factor at a time, take the sum, right? So that will give you t times, so minus lambda I times so we are only differentiating the ith factor, and I is 1 to n here, that's the sum. Right. So yeah, any questions about this? So we have differentiated and then multiplied by t just to write a better expression, and so once you do this, it will be better to actually re-express the RHS as a sum of fractions. So let us bring out the full product and be left with minus lambda I divided by 1 minus lambda I t. Right. So that is what we are left with, and there is this full product. Now what? So now you observe that 1 minus lambda I t, its inverse, exists in the power series, ring. So you expand that out. So 1 minus lambda I t will expand as let me absorb the t first. This now, it's just this double sum, right? Is this right? And there will be a hanging minus sign. Yes. So basically you get in the inverse you get 1 plus lambda I t plus lambda I t whole square dot dot, and there is a lambda I t already sitting outside, so take it inside. So your series starts with lambda I t and then its square cube, and you are summing it up, and then for various i's you take the sum, so it becomes a double sum. So this technically this is actually happening in the power series ring. So this power series ring is you can take complex over rationals. So this is this ring. So if you want to be technical about where does this computation happen, so it is happening in the power series ring. So in this power series ring, basically the elements of this ring are infinite sum of t monomials, but taken in this increasing order. So the bigger the power of t is, the smaller that term is considered. Okay, this is the algebraic version of analytic power series. So this is called formal power series. Okay, so in this power series we have these two expressions LHS and RHS, and then we should compare t monomials, right? So we'll do that, but let us first bring it in a form that we want. So let me now. Okay, so this part, right? This is just sigma lambda I to the j, which is, I mean, okay, we have to swap the sigmas. So let us first swap that. So let us have this thing as. Okay, let me just write the expression before giving the explanation. That is the expression. So this double sigma, you can swap the sigma, and then you are looking at sigma lambda I to the j for all these i's, right? That is pj. So the coefficient of t raised to j is just pj. So that gives you this term. And next you look at the product of 1 minus lambda jt right, which before just this. Look at the coefficient of t raised to I there, and that is just the elementary symmetric sum with the appropriate sign. So yeah, you have now these two polynomials. Well, first one is infinite, but we'll only go up to t raised to n because there is no point going beyond. So you have now these two polynomials and their product is equal to LHS. So now you should just simply compare the t raised to k coefficients, and when you compare you will get to this. So let us just write it in terms of t raised to k So minus, if you look at the coefficient of minus t raised to k, what you will see is this. Okay, so this part is the coefficient of minus t raised to k above. So to get t raised to k, you have to look at j and i's whose sum is k, right? Because you have this term t raised to j here and t raised to I here. So you need to look at those j and i's such that j plus I is k. So so that will be j and k minus j. So j will give you pj, and the k minus j will give you ek minus j with the sign. That's the sum, right? So now when you compare the coefficients of minus t raised to k both sides, you get Newton identity as claimed. So now finally compare minus t raised to k coefficient both sides. Okay, that is the proof. Any questions? So yeah, that should already convince you that determinant is in VP, right? Because we have related the determinant, which is product of lambda i's, to a polynomial in the power sums. And this is a very simple expression. The recurrence is very simple. It is easily implementable as a circuit, small poly size. And the final point is that the power sums are trace of matrix powers, and matrix powers fully can be computed again as small circuits, poly n size circuits. Okay, the poly n size part should be clear. So we have shown the determinant is in VP. So this finishes the proof of determinant in VP. Okay, so that much we have already done. Any questions about this statement? But this doesn't stop here. This is actually giving you a lot more. So this analysis actually gives you a practical implementation for determinant that is extremely fast in the parallel sense. Okay, a parallel algorithm is obtained. So I will not go into all the details. Maybe I will put it as an in the assignment. But so one observation is that the recurrence that you have got, right? So it is you can think of it as, so you are interested in elementary symmetric polynomials. You are interested in E1, E2, E3, finding them, and the recurrence is actually giving you a linear system to find them, where the entries are. So well, E1 is the same as P1, so you have P1 here, and let's say we just put P1, P2, P3 here and so on. So E1 is P1, which is, that gives you the first row from the recurrence, using the recurrence. Then the next recurrence for k equal to 2 tells you that P2 is, so E1 P1 minus 2 E2 and then 0. Then the third recurrence for k equal to 3 gives you P3 is equal to E1 P2 minus E2 P1 plus 3 E3. Okay, so if you look at this just the 3 by 3 part, what do you see? This is the matrix. Why is it special? Well, it is a lower triangular matrix, right? So you have a linear system where the e's are the unknowns. So this is what you want to find. These are the unknowns. And to solve this linear system, you have to invert the triangular matrix, right? So it actually boils down to the inversion of the triangular matrix, and you want to make this implementation faster. So there is a very nice way to invert triangular matrices. So you write your triangular matrix as a diagonal matrix plus a nilpotent matrix, and you want to compute this. So this is diagonal and this is nilpotent. Nilpotent because if you raise it to, let's say, the dimension of the matrix, it vanishes. Okay, so how do you compute D plus n inverse in a fast way? And usually inversion of a matrix is pretty complicated because you have to at least compute the determinant, which will put us in a vicious cycle because our goal was to compute the determinant, and now so inverse also will, so somehow you have to break this cycle. So you have to find a different way to compute this inverse, which will be, yeah, so the amazing thing is that this also can be done using power series. So the same power series. So one, think of this as 1 minus n inverse, and that is equal to 1 plus n square plus n cube dot dot, and after a point it vanishes. So this actually is this is essentially sum of powers of n, something like this. So you just have to compute the powers and then sum them. Okay, so this is the idea. This is why solving the linear system actually does not need determinant. It can be done just by powering and addition. And when you formalize this, when you do this implementation, now actually it is, after this point it is quite straightforward. Once you do this, you will see that even the depth of the circuit is very limited. Okay, and that gives you a very fast parallel algorithm to compute determinant. So as you saw here, we started with this abstract looking model, and we proved this statement that determinant is in VP, but the proof of it is actually giving you even a new way to compute determinant in practice, which is extremely fast and which you cannot guess it at all from looking at the definition of determinant. Okay, so yeah, so this implementation details I leave for the assignment. Is Schoenhaga's idea. Implements this to get a fast parallel computation of determinant. And no big constants are used, although VP allows the use of arbitrarily large constants, but in this proof you are using very small constants. So the theorem that you will get is that the depth is only log square n, the size is only poly, for determinant n. Okay, so let us just state it as a theorem that determinant n is in Vp, that is actually depth log square n, and another qualification is that as you vary n, can you describe the circuits? Because in the definition of Vp, that is left totally arbitrary. There may not be any connection between the circuit for n and the circuit for n plus 1. Right? That is the built-in non-uniformity in Vp. But that is not what this proof is giving you. So here the proof is actually giving you an explicit fast way to compute the circuits, describe the circuits as well. So it is P uniform. Okay. And another point here is that this depth is actually with the fan in and fan out 2. So the fan in and fan out is also very small. Okay, it's constant. Depth is just log square. Every circuit for a given n, the circuit can be computed by a Turing machine in polynomial time. Okay, so this is this gives you everything except maybe some, you might expect some more improvements, but other than that, asymptotically it is giving you, or functionally it is giving you the best possible results for determinant. You may ask whether log square can be reduced to log. You can ask whether the size is, if it is n to the 5, can it be reduced to n square? So those questions you can still ask, but yeah, even this is quite a strong thing for a polynomial like determinant. Right, so the proof is as we have already sketched. So we leave the size and depth analysis. As an exercise. And so key ideas are to compute n powers. And the second idea is to solve a triangular matrix equation. Triangular linear system in lowest depth. Which is also the in parallel time. The parallel time complexity should be very fast. Fine, so this is yeah, so we showed determinant in Vp and more.
So what would be P non-uniform if we know for n and we cannot extend?
There is no fast algorithm as in the sense of Turing machines that can produce the circuit in poly n time. So it may need exponential in n time. I mean, within exponential in n time, I think you that is a lot of time. That kind of uniformity, I think you always have. But the thing is whether there is a polynomial time algorithm which, when given n, or to be formal 1 raised to n, when given n in unary, then it outputs the nth circuit. So the circuit building should not be left to the user, because that could be again that is extremely hard. How do you come up with a circuit for a given n? If n is 1 million, how do you come up with the circuit that is running on 1 million inputs. So that also somebody has to provide it. So is there a Turing machine that can do it in a fast way? But for the definition of VP, that was left free, that was left unfixed. In the case of determinant, we are actually getting this additional property, which is why all these things are good in practice. But now we will actually go through a different route and prove something even better for determinant. Okay, so we'll actually define a complexity class based on determinant. Okay, so any polynomial that you can compute in that class, you can reduce it to determinant, and you can also compute determinant in that class. So we'll actually make this really optimal. We'll come up with a class that is determinant hard and complete. So do you know the name of this class? Right, so this is called arithmetic branching programs. So determinant is closely related to an important polynomial representation which will be different from circuits, formulas, and so on. It's a completely different representation defined in a different way. It is called arithmetic branching programs. So ABP. So you might have heard the term branching program. There are also Boolean branching programs. This will be obviously inspired from that. It will be a arithmetic version of the Boolean branching programs, but it will have a lot more structure. So this is basically a layered graph. You can think of it from going from left to right. So the computation moves from left to right. In every step there are layers. It's a layered directed graph. So an ABP is a layered directed graph with source and sink. Source vertex is called S and sink you can call T. Now edges from layer I to layer I plus 1 are labeled by a linear polynomial. So the linear polynomial you can assume is in n variables, field f. Okay, so you have these edges going from the source to the sink, and when you are at level layer I to layer I plus 1, you will draw edges. The edges will have labels or weights, which is a polynomial, say x1 plus x2. Could be one weight or just x1 or maybe 0 or 1. Okay, can also be field constants. Yeah, so once you have this picture, what do you think is the polynomial that this computes? How should you define the final polynomial that you get at the sink? Right, so in a path from source to sink, whatever linear polynomials there are, you take the product, and then for every path from source to sink, you add these products. That is the polynomial. So the polynomial computed at sink is f, which is take a path from the source to the sink, so gamma from S to T, and weight of gamma, compute the weight of gamma, which is just the product, so product of edge weights. In gamma. Right, so that is it. ABP, source, sink, you have layers, you have linear polynomials as labels, and finally the polynomial computed is just this f. Yes, so it is, I mean, I don't want to see it as a circuit yet, but this expression for f is sum of product of linear polynomials. So it's sigma pi sigma. These are the three operators you are using in this order. And then what are the parameters or resource parameters for this? That when will you say that the ABP is small? Well, obviously when the graph is small, only then should you say that the ABP is small. If the graph is large, then it's a large representation. So that is one thing. Size of the graph is one parameter. Size of ABP, that is one thing. The second thing you can look at is in the ith layer, how many vertices do you see? So maximize over I. So that is called the width of ABP. So max number of vertices in a layer. And finally depth, how long is the ABP? So depth is the longest path from source to sink, right? So first you want to optimize the size, or well, not optimize as in, say for n variate polynomial you want an ABP of size poly n. That would be the ideal goal. Once you have that, then you can talk about other things like can I make the width small, can I make, I mean width small as in can I make width, let's say 3. Obviously it is poly n, but can I make it even smaller, can I make it 3, can I make it 10, and depth here, but that, so depth is usually correlated with the size, we don't do much with the depth, but we talk about size and width most of the time. Okay, so we'll see an example and do it study this next time. Any questions? Okay.